Hello and welcome to another calculus video. In this one, we're going to look at section 3-2, Rolle's theorem, and the mean value theorem. Bullet points are pretty simple. Understand and use rolls. Understand and use the MVT. Now let me start this by doing this. Here I got the first quadrant of the Cartesian plane, and I'm going to say my function f of x is going to be continuous. I'm going to have to draw it without lifting my pencil from the pad, and my interval is closed from a to b. Now let's say a gives us an output here. That's f of a. And let's say b puts us way up here, as long as f of a and f of b are not equal. So over here on the y-axis, there is a gap between them. Now, I can pick any value in between these, and I'm going to just call it f of c, and I'm going to make a dotted line. And I would ask everybody to visualize, can I connect the black dots without crossing the blue dotted line? It's going to be impossible. Again, my function is continuous, so I cannot lift my pencil from the paper. I could try to go way over here and sneak over at the last minute, but I crossed the blue dotted line. I could try to get it over with real fast, but I crossed the blue dotted line. I could try to wait for the middle, but I had to cross the blue dotted line. So it is impossible for me to not cross the blue dotted line as I go from point f of a to f of b, and that tells me wherever I cross, there is some c in this interval in between a and b, such that it's going to give me the output of f of c. And I could make f of c, my blue dotted line way up here. I could make it real close to f of a. I could put it anywhere in there. So the big idea is, this might take me a while to back up, because the function is continuous and our interval is closed, as we achieve every input between a and b, and there's infinitely many of them, we are going to achieve every output between f of a and f of b, if not more. We're at least guaranteed every value between f of a and f of b. And that's kind of a good intro here to Rolle's theorem. But let's read what the book says. The extreme value theorem, back from the previous section, states that a continuous function on a closed interval from a to b must have both a min and a max on the interval. Both of these values, however, can occur at the endpoints. Rolle's theorem, named after the French mathematician Michel Rolle back in the 1600s, it gives the conditions that guarantee the existence of an extreme value in the interior of the closed interval. So as opposed to having one at the endpoints, Rolle says you're guaranteed a min or a max on the inside. And here is the setup to Rolle's theorem, and this is why we just did this on the previous slide here. Our conditions are, let f be continuous on a closed interval, and it's differentiable on the open interval. Remember, we can't derive at the endpoints maybe, but everything in between is differentiable, so that tells us it's a nice, smooth, flowing curve. If f of a is equal to f of b, then there's at least one number in that interval such that the derivative will equal 0. So this, we're going to take the initial picture I did earlier. We're going to change a little thing on that. So here's our xy axis, and here's a, and here's b. That is the endpoints of our interval. And now here in this setup, they tell us f of a is equal to f of b. So let's say my a value is right here. Oops. So this would be f of a. And my b value is exactly the same. So it's at the same height. So this f of a is also the same, as f of b. So this says our function's continuous, interval's closed. If f of a and f of b are equal, there is at least one number c somewhere in between. I'm just going to put it right here. In between these points, there's got to be a c value that would have a derivative equal to 0. And what does the derivative equal to 0 tell us? That means it's going to have a horizontal tangent line. The derivative, remember, tells us slopes. I should put f prime of c. Derivatives tell us slope, and if the slope is equal to 0, then that means we have a horizontal tangent line. So imagine, can I connect these dots without having a spot that would have a horizontal tangent line? Well, if I go up and then back down, I'm going to have a peak. Horizontal tangent line is going to be there. If I try to sneak in underneath, I have a valley, and somewhere in that valley is going to be a spot where there's going to be a horizontal tangent line. I could try to be sneaky and just go straight across. Well, now every single point would have a horizontal tangent line. So we're guaranteed if our endpoints are at the same height, f of a and f of b are the same, we're guaranteed some number in there is going to have a derivative equal to 0. Again, so the interior is going to have a min or a max. We know it's not going to be at one of the endpoints. And this is Rolle's theorem. So from Rolle's, we can see that if function f is continuous on our closed interval and it's differentiable inside that interval, and if our endpoints are at the same height, f of a and f of b, then there must be at least one x value between a and b at which the graph will have a horizontal tangent. When the differentiability requirement is dropped from Rolle's theorem, f will still have a critical number in there, but it might not give you a horizontal tangent line like we see here in this picture where we have a cusp. The cusp, it's continuous, would still be a max, but we would not find it by a derivative being set equal to 0. And next, example 1. This is a very nice straightforward illustration of Rolle's theorem here. Find the two x-intercepts of this function and show that the derivative is equal to 0 at some point in between. Well, now the first part is not even a calc question. We want the x-intercepts of this quadratic function. How do we find x-intercepts? We set our function equal to 0. And this one will factor nicely. We need two numbers that add up to -3 multiplied to +2. That's got to be a -2 and a -1. And if we set each of those to 0, we get x equals 2 and x equals 1. Okay, so these are our x-intercepts. And actually, these set up the first part of Rolle's theorem. We know that f of 2, that's a terrible looking 2, f of 2 is equal to 0, and f of 1 is equal to 0. So now Rolle's theorem says somewhere in between 1 and 2, we're going to have a derivative with a horizontal, or a spot where there would be a horizontal tangent line. So let's derive f prime of x, nice easy derivative, 2x and a -3, 2 derives away. And how do we find horizontal tangent lines? We set our derivative equal to 0. And when we solve this, we're going to add 3 and divide by 2. So x equals 3/2. Now think about that. When we did our endpoints, our interval was 1 to 2 from our x-intercepts. This number is where our horizontal tangent line would be, and that is right in between 1 and 2. So now think about this, x squared, it's a positive x squared, so what we have is a parabola opening up. And the first thing we did is found the x-intercepts by setting our function equal to 0. So there is our f of a is equal to f of b. They're both equal to 0. And we took the derivative and set it equal to 0, and we found 3/2, and that number is right in between 1 and 2. And that's where our horizontal tangent line would show up. Okay. Rolle's theorem, illustrating Rolle's theorem, example 2. Rolle's theorem states that when f satisfies the conditions, there must be at least one point between our endpoints a and b at which we have a 0 derivative. There, of course, could be more than one such point, as we are about to see. And I shouldn't have spoiled that with the graph. So our function is now x to the 4th minus 2x squared. Find all values of c in the interval -2 to 2, such that f of c is going to equal 0. Now first, just to make sure that Rolle's theorem is going to apply, we're going to check our endpoints. We're going to make sure that f of a does equal f of b, because if that's not the case, we cannot use Rolle's theorem. So we're going to check our endpoints. F of x, we're going to check -2 and 2. So we're going to do f of negative 2. That's a terrible looking 2. F of negative 2 is going to be negative 2 to the fourth minus 2 times negative 2 squared. And what's that going to be? Negative 2 to the fourth, that is 16. And then here we'll square that to a 4. Minus 2 times 4, that's minus 8. So 16 minus 8 is 8. So f of negative 2 is positive 8. And then f of positive 2 is going to be the same thing, because now remember the negative got squared away in each of those. So if we plug in the positive 2, we're going to get 16 minus 2 times 4. 16 minus 8 is 8. So here we can see f of a is equal to f of b, and our function is continuous, our interval's closed, so we can say that Rolle's theorem applies. Rolle's applies. We are allowed to use Rolle's theorem. Okay, so the endpoint's checked out. We know that we're legally allowed to use Rolle's theorem. So let's derive. F prime, simple power rule, is going to give us 4x cubed minus 4x to the first. Remember, we're looking for horizontal tangent lines, so we set our derivative, our slope function, equal to 0. Horizontal lines have a 0 slope, and now we're going to solve that. Start by factoring out a 4x, and that'll leave us an x squared minus 1. And if we set 4x equal to 0, we get x is 0. And if we set this equal to 0, add 1 and take the square root, we will get plus and minus 1. Okay, now let's see what happened here graphically. I always like to tie this back to the graph. Here's the graph of that function. And the first thing we did is checked the endpoints. We put in negative 2, we got an 8. We put in positive 2, we got an 8. So Rolle's theorem is going to apply. Oops, let me get back there. Where'd that go? Rolle's theorem, remember, the endpoints must be the same height, so f of a and f of b check out. And now we can find where the horizontal tangent lines would be. And when we derived and set it equal to 0, we got 0 and plus and minus 1. So here at the origin, we've got this little peak. That would have a horizontal tangent line. And then at 1 and negative 1, we have these sort of twin valleys here. Each of these would have the same horizontal tangent line on the bottom. So there are, again, 3 spots where we have horizontal tangent lines in the middle. Remember, we're guaranteed at least 1 by Rolle's theorem. Here we actually found 3. Got a nice bonus. Always be careful of technology. They're great when they work, but there are some flaws in there. It says a graphing utility can be used to indicate whether points on graph in examples 1 and 2 are mins or maxes of the function. When using a graphing utility, however, keep in mind it can give you misleading graphs. For example, if you use a graphing utility to graph this, most viewing windows, it appears to have a max at 1 when x is 1. So you see 1 here. It kind of looks like we have a peak there at 1. But if we evaluate the function at 1, we'll see that f of 1 is equal to 0. You know, if we put a 0 in here for all of these x's, it looks like f of 1 is equal to 0. So to determine the behavior near that x value, would need to examine the graph analytically to get the complete picture. So again, you're not going to be able to see this on a calculator. Imagine 1 pixel is taken away from that peak and dropped down to 0. So again, be extra cautious when using those TI-89s or other graphing utilities. They're not perfect. Ooh, now before we talk mean value, let me go back and point out one other thing on Rolle's here. When we set up Rolle's theorem, notice our endpoints f of a and f of b, they're on the same height. So if I did connect these with this black ink line, the slope of that line would be 0. And then later on, we set our derivative also equal to the same 0 because the slope between the endpoints would be horizontal. We're looking for a tangent line that is horizontal, so we set our derivative f prime equal to 0 because we wanted a horizontal tangent line, and imagine it would be parallel with this horizontal line drawn through our endpoints. When we look at mean value, we're just going to take rolls and slant it. We're going to tip rolls to an angle. So Rolle's theorem can be used to prove a higher order theorem, another theorem, mean value. Now, mean value starts off kind of the same. If our function is continuous, our interval must be closed and differentiable. Then it says, then there must exist some number c in between a and b such that f prime of c, the derivative, is equal to this, f of b minus f of a. And let's see, look at this. Here we go. So this part here, oops, let me get that out of there. F of b minus f of a over b minus a. Well, here's a and its output f of a, and here's b and its output f of b. So what this is the slope of the secant line. Slope of secant line. And notice if we have the points a and f of a and b f of b, we could just use the good old slope equation from Algebra 1. We're going to find the slope of this secant line. And then we're going to take our derivative f prime and set it equal to that slope. So again, in Rolle's, we're setting our derivative equal to 0. In a mean value theorem problem, we're going to find the slope between these 2 points, find that slope, m equals something, and we're going to set f prime equal to that same slope. Again, oops. Yeah, if I tip this a little bit and I make this line horizontal, for Rolle's theorem, the endpoints are at the same height. The line between them would be slope 0, so we set the derivative equal to 0. Now we're sort of going to tip Rolle's this way, and now it's mean value. So if we find the slope between these points, we're going to set our derivative equal to that slope. And if you're still a little confused, maybe our next example is going to clean that up a little bit. But first I put this in here. Let's read it. Although the MVT can be used directly in problem solving, it's more often used to solve or prove other theorems. In fact, some people consider this to be the most important theorem in all of calculus. It's closely related to the fundamental theorem that we're going to see in the next chapter. For now, you can get an idea of the versatility of mean value, blah, 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 blah. Don't worry about it. Here we go. For f of x equal to 5 minus 4 divided by x, find all values of c in that interval from 1 to 4 such that the derivative is going to equal this slope, f of 4 minus f of 1 over 4 minus 1. So let me just do this. Here's our function f of x equals 5 minus 4 over x. So we're going to use the endpoints of our interval, 1 and 4, to nail down a couple points. First, let's find f of 1. If we plug a 1 in there, we get 5 minus 4 over 1. That's 5 minus 4, or 1. So we get the point 1, comma 1. Let's check the other endpoint, 4. F of 4 is 5 minus 4 over 4, which is 5 minus 1, or 4. So we've got another point, 4, comma 4. So now here, f of a and f of b are not at the same height. You know, this right here, if you do this little piece, we'd know right away this is not a Rolle's problem. This is mean value. If these outputs are the same height, we're going to use Rolle's theorem and set our derivative equal to 0. But since these come out to be different heights, we're not going to set our derivative equal to 0. We're going to find the slope between these points and set our derivative equal to that. So let's find the slope between our endpoints. So our slope equation is y minus y over x minus x. So here's my y values. I subtracted in this order, 4 minus 1 for my y's, and in the same order for my x's, 4 minus 1 for my x's. So I get 3 over 3, or my slope is equal to 1. Now again, in rolls, we would derive and set our slope equal to 0. In this case, we're going to derive and set our derivative equal to 1. So we're going to set f prime equal to 1 as soon as we get that derivative. So before we derive, I'm just going to do a quick rewrite, make this as a 4x to the negative 1. Now let's derive. Simple power rule here. 5 derives away. Here we're going to have the negatives are going to multiply. That's going to turn into a positive 4. And then it's going to be x to the negative 2. And let's get rid of the negative exponent by putting it down in the denominator. So now here's our derivative. If we were in a rolls problem, we would set our derivative equal to 0. But this is mean value. So we're going to set this derivative equal to our secant line slope 1. So if we set this equal to 1, let's solve it. Well, to get the 4 alone, let's multiply both sides by x squared. So we get 4 is equal to x squared. And if we take the square root of both sides, we're going to get x equals plus and minus 2. Now be careful. If this is especially on the AP test as a multiple choice, a decoy answer would be both positive and negative 2. But look back to our interval, 1 to 4. The positive 2 fits in there. Negative 2 is outside. So the only answer that's going to work is positive 2, at least for the interval that we're dealing with. Okay. What do we got next? This is a good one. Example 4. I've seen these speed traps where I grew up in Erie. They do them in a much smaller scale, though. But it says here you've got 2 stationary patrol cars. They're equipped with radar guns, and they're 5 miles apart on a highway. Let me bring down the figure. So here's our 2 cops. The first one's sitting here. Second officer is 5 miles away. They both have radar guns. A truck passes the first patrol car, and that guy clocks it at 55, well below the speed limit. 4 minutes later, the truck passes the second car. Its speed is clocked at 50, so it looks like he's slowed down. But we can mathematically prove that that truck must have exceeded the speed limit of 55 at some point during that journey. So if this problem is Rolle's theorem or mean value theorem, we have to start out with a couple of points because we need to find the slope between them. It might be 0 or it might be some other slope, but we need that to figure out what kind of problem we're dealing with, Rolle's or mean value. So in this case, let's see, instead of x comma y, we're going to do t for time, and I guess the other one would be distance traveled, time and distance. So let's see, let me drag the picture back out. So let's see here, and I guess we always use S for position. So I guess T comma S work. It really doesn't matter. So let's see. When the problem begins when the truck passes the first patrol car. So our first time value is going to be 0. And then how far has the truck traveled past that first cop? 0. So our first point is 0, 0. Now let's see later. 4 minutes later, so time is now 4. Hold on, let's back that up. Let's not use minutes because the problem is context per hour, 55 miles per hour, 50 miles per hour. So let's keep everything in hour units. If we have 4 minutes out of a total 60 in an hour, we could divide by 2, so that would be 2 over 30. And they're both even divide again, 1/15. So let's make our t value here 1/15 of an hour. And then our S value here is how far past the cop we are. At time 0, we were just passing the cop. 1/15th of an hour later, we've moved 5 miles. So there's our S value for the second point. So let's see. We are at different heights. Our outputs are at different heights. So this is not rolls. This is going to be a mean value theorem. And if we find the slope of these between these 2 points, that's going to be the average value over the interval. So let me get this picture out of the way. Let's find the slope between these points. And I'm just going to subtract this way. 5 minus 0 upstairs is 5. 1/15th minus 0 is 1/15th. And now remember, up here, this 5 would be over 1. Let's bring up, flip, and multiply. So that's 5 over 1 times 15 over 1. So if we multiply straight across, we get 75. 75 miles per hour. So again, when the truck goes past, whoa, get back there. When the truck goes past the first cop, he's doing 55. Goes past the second cop, he's slowed down to 50. But what we've just proven here, at some point in between those officers, the truck had to be doing 75 miles per hour. Because what we did, if I draw a graph of this, and I'm going to sort of draw it pretty extreme. And let's even do, the scaling on the y-axis. I'm going to make it down low here. This is 50 miles per hour. So at time 0, the trucker was doing 50 when he passed the first cop. And then here's our time axis. 1, 2, 3, 4, 5 minutes later, he was just up to 55. Or was that in reversed? I think it was 55 first. Yeah, 55 first. Oops. So the first dot is up. Whoa, dot is up here. And oops, let me back this graph up. It might be easier to see it this way. Whoa, whoa, whoa. There we go. When we figured out our end points, that should have been the same color. But we had 0, 0 and 1/15th, 5. So if I plot those points, here's 0, 0. And then I'll make this, if we go way out there, would be 1. So I'm just going to make this my 1/15th. And that would be way up at 5. So what we found here was the slope between those points, and that was 75. And this is an average rate of change across the interval. So remember when the first cop saw him, he was doing 55. Later, the second cop saw him doing 50. Well, his average rate of change between the cops had to be 75. So we know he did at least 75 at some point. He must have done more than 75 if that is his average. And, this is enough. They could take this to court, and a judge could be agreeable that they could prove mathematically that the trucker was doing more than the speed limit at some point. They don't know exactly when or exactly where or for how long, but you can mathematically prove that the driver broke the law. And it says here, a useful alternate form of the mean value theorem is this. If f is continuous on our closed interval, it's differentiable inside the interval, then there exists some number c in the interval such that f of b is equal to f of a plus b minus a times f prime of c. And if that's a little confusing, let's just see what happens if we try to get this f prime alone. The first thing we would do is subtract f of a from both sides. So f of b was over on the left. We're going to minus f of a. And now that's attached to this f prime of c, so we're going to divide by b minus a. b minus a equals f prime of c. We've seen that before, just that alternate form of the derivative, or the definition of that mean value theorem. The f prime is set equal to this slope. And that is it for this section. It says here when doing the exercises, keep in mind that all polynomial functions, rational functions, and trig functions are differentiable at all points in their domains. You know, there are some numbers that are excluded from domains, especially some of the trig functions and rational functions, but within their domains, they are completely differentiable. So I will see you in class.